All right, so today we are moving on to some stuff that maybe you saw in high school, maybe you didn't. I don't know, depends on where you went to high school. Starting on Wednesday, we will be doing reactions that occur in solutions, okay, otherwise known as solution chemistry. And solubility rules will be a big helper for us in that part of the course. So we need to have solubility rules is something we understand. Okay? Now in this class, in Gen Chem 1, we're going to say soluble, not soluble, right? Black and white. There's no in between. It's either soluble or it's not. The reality is every substance is soluble to some degree, right? It might be very, 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 very small degree, which is why we're calling it insoluble in this class. But the reality is there's a big gray area. Okay, it's not just black and white. The area between it is called equilibrium. Okay, and we'll get into that in Chem 2. But right now we're just saying, yes, it's soluble, no, it's not. But just know in the back of your mind that all of these things that we're calling insoluble do actually dissolve. It's just a very, 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 very small percent. Okay, and we'll learn about what percent that is next semester. So here are your solubility rules. They're on page 108 in your textbook. And how do you use the solubility rules? Well, you look at the compound of you look at the formula of the compound, and then you look to see if those substances are appearing here on the soluble list. So all of these will be soluble except, right? Or you look to see if it's on the insoluble list. All of these will be insoluble except. Okay, does everyone understand how it works? I put a couple of notes for you down there at the bottom of the page too. So soluble means you can't see it, right? If it's dissolved, you're not able to see it unless the ion just has a color to it, right? Copper 2 is blue. So if copper 2 is dissolved, the whole solution will look blue. Think back to lab last week. So this one will be soluble. If you have an insoluble substance, that's called a precipitate, right? So you see a precipitate where the whole thing looks, sometimes the whole thing might look cloudy. So if it turns like a milky color, looks like milk. Here, this is AgOH, right? So that's why it's brown throughout. But if it were a white precipitate throughout, it'd look kind of a milky color. This one's soluble, no precipitate, it's just yellow. Insoluble, insoluble, insoluble. Right? This one will be soluble. All of these will be insoluble. Okay, so we're going to spend a lot of time beginning on Wednesday doing solution chemistry. And like I said, a precipitate forms immediately, right? When you combine two solutions and something that's insoluble forms, you see that reaction pretty much right away. So use your handout and just shout out your answer. Decide if these substances are soluble or insoluble. So you can look it up by the cation, you can look it up by the anion, or maybe in some situations you could look it up by both. Would you expect Cobalt 2 hydroxide to be soluble or insoluble? What do you pick? Anyone brave enough to say it, knowing that the camera's running? Yes, it is insoluble, right? So you could try to look it up by cation, but Cobalt 2 isn't listed here, right? Cobalt 2 isn't listed. Hydroxide, however, is, right? It's listed under the insoluble compounds. Most metal hydroxides and oxides are insoluble, with the exception of alkali metal, that's group 1. Cobalt is not in group 1. Barium, strontium. Cobalt isn't barium, cobalt isn't strontium, right? So therefore, this is an insoluble salt. Barium nitrate, soluble or insoluble? This one's soluble, right? Nitrate is listed under soluble compounds. All salts of NO3 minus. No exceptions listed, therefore this one's soluble. What about ammonium phosphate, soluble or insoluble? That one's soluble, and you could look it up by either the cation or the anion here, right? If you look it up by cation, NH4 plus, no exceptions listed. Or if you look it up by phosphate, phosphate's listed under insoluble, but NH4 plus is listed as an exception. Okay, so you could look this one up by the cation or the anion. You'll come to the same conclusion anyway, either way. Do we understand how to do this? Now we're going to kind of set the solubility rules off to the side until Wednesday. So don't lose that page. We're going to come back to it on Wednesday. Today we're talking about solution concentration. Solution concentration. And so there are 3 vocab words we need to refresh our memories on. First one is unsaturated. The name unsaturated implies that it's not maxed out, right? It contains less solute than the solvent has the capacity to dissolve. That's the technical definition. What does that mean? It means your solution can still dissolve more. Your solvent can still dissolve more, okay? So for instance, if I've got my bottle of water here and I take just a teeny little amount of sports drink, let's say a big blue, right? So a teeny little bit of blue sports drink mix in it. I shake it up, right? The whole thing would turn light blue, but this is unsaturated, right? I could still get more to dissolve, okay? So in an unsaturated solution, you have not maxed out the dissolving capability of the solvent yet. So you can still dissolve more. All right. So if you're making your hot chocolate, or not hot chocolate, let's pretend, because hot chocolate you typically use the powder, right? So let's pretend that you're making chocolate milk and you pour a teeny little bit of the chocolate syrup in and you stir, 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 right? Just a teeny little bit. You can still dissolve more. That's unsaturated. Now saturated contains the maximum amount that will dissolve at a specific temperature, okay? I say at a specific temperature because there is a third level of saturation we can talk about, but we have to change the temperature to get to it. So if you're adding your chocolate syrup to your milk and you're stirring and stirring and stirring and stirring and stirring, and you notice it's starting to accumulate on the bottom, right? It's no longer dissolving. If I let my kids make their chocolate milk, that's what they would make, right? It's probably what I would make too. It's delicious, right? If you've got so much that's accumulating on the bottom, it's no longer able to dissolve, right? You've saturated the solution. You've maxed out the amount of dissolving that that solvent is capable of doing. Now there is a cheat. You can get around this. So if you're taking regular cold milk from the fridge and adding chocolate syrup to it, right, and you want even more to dissolve, turn it into hot chocolate, right? If you increase the temperature, now you can dissolve even more, okay? But you have to cheat in order to get to it. So if you are, let's just pretend I'm adding sports drink beverage to this, right? Pick your favorite flavor. I'm adding. It's all accumulating. Okay, I can't get any more to dissolve. Boy, I really want a super saturated sports drink. Pour it into a beaker, put it on the Bunsen burner. I could increase the temperature, so I have to increase the temperature in order to get this to happen. Now I get it to dissolve. Now, the problem with this is, yes? That's the problem, right? They're unstable, pretty unstable. And I don't mean unstable in the sense that it's going to explode in your face, okay? What I mean is it's not going to take very much to get all that solute to come back out, okay? So here's a little picture. It looks like they're putting a crystal in, just a small little salt crystal or something, right? If a substantial piece of dust falls in it or you bump it hard enough, okay? Once it cools down, it'll stay dissolved so long as it stays still. But even if it doesn't stay still, sometimes it just sits there long enough, it'll crash back out. And so you put a little disturbance in the force, and now all that solute comes back out. Okay, so they're not unstable in the sense of what you think when you hear the word unstable, right? You hear chemically unstable, you're like, that's what you think, right? It's not going to blow up. It's going to not remain dissolved. It can come back out pretty easily. Does this make sense? Levels of saturation. So we're not going to be making supersaturated solutions. It's not something that's practical to us, but just so you know what they are. So today, for the rest of the time, we're going to talk about concentration. Solution concentration. So concentration is just the ratio of solute to solvent. There are lots of different units that we use to express concentration. So far, we've discussed molarity. Right? We did molarity way at the beginning of the semester. And I warned you that another one was coming down the pike soon that sounds and looks very similar, but is completely different. Right? Molarity, capital M, that's why I underline it, versus molality, little m. That's why I do not underline it. So if you're one of those people who rounds all your numbers and your letters, right, you need to find some way to distinguish molarity from molality, because this is capital M, right, pointy, whereas this is rounded. Percent by mass, percent by volume, those are two really easy ones. And parts per million and parts per billion are pretty easy too. So basically, if you could make it through molality today, that's the toughest one we're going to do, because you already know molarity. So let's review molarity just to make sure we remember. Molarity is moles per liter. right? Mole solute per liter of solution. This is not going away. We're going to have molarity with us till the end of the class and then next semester in Chem 2, right? It's never going away. So get used to seeing it, get used to writing it. And again, please do something to indicate that it is a capital M, not a lowercase m, because molarity and molality mean two very, very different things. Okay? We're going to be using molality calculations in 2 weeks when we do colligative properties. So we're talking about them now. We'll come back to them in a couple weeks. The most common mistakes I see with molarity, converting grams to moles, and then if the volume is given in milliliters, you got to convert that to liters, right? Those are the two most common molarity mistakes I see. So you just do this one, remember, see if you remember how to do it. Hopefully the answer is yes. What is the molar concentration? That should tell me that my units are in molarity. What is the molar concentration when 2.5 grams potassium chloride dissolves in 500 milliliters of water? Take a minute and try this one. I'm going to pause the recording while you do. All right, let's go over the answer. Hopefully this was not too difficult of a calculation because we've been talking about molarity for a while now. All right, you've got to convert grams to moles, carrying out extra decimal places because we're going to round at the end. All right, so when we convert grams to moles, we're rounding at the end, so we're carrying out extra digits here. 500 milliliters needs to be converted to liters, right? So that's 0.500 liters. In terms of sig figs, I rounded 2 significant figures, right? Because I've got 2 sig figs here, 3 sig figs here, so I can only keep 2 significant figures in my final answer. For my units, you write capital M, or if you don't trust your ability to write a capital M that doesn't look like a lowercase m, you could write out MOL/L. That's perfectly acceptable as well. And that would remove any ambiguity, right? Because your units are moles per liter. So you could write out MOL/L. That's acceptable, okay? Because we call capital M MOL/L. So either one works. Do we remember how to do this? You feeling good about molarity? All right. Now, again, if you need more practice on this, I don't know if you know this or not, but in the syllabus every week, so we're on week 7 now. For every week of the semester, I have suggested problems from the textbook. So you can do those. The odd numbered answers are in the back. I also post problems online with the answer keys, and then you can always email me and just request more problems, and I can make some up for you. Now let's talk about the much awaited molality. Molality is little m. Now the numerator is the same. In both molarity and molality, it's both moles on top. What's different is the bottom. In molality, it's moles per kilogram. Moles per kilogram. Molality is moles per kilogram. So that means that whatever your solvent is, if it's given to you as a volume, you're going to have to find a way to turn it into a mass, right? Molality is moles per kilogram. So let me ask you, let's pretend that I have my bottle of water here. This is a 500 milliliter bottle. It's about, I don't know, 150 milliliters left. Okay, so I've got 150 milliliters of water. And I want to know how many grams is that? How could I turn a volume into a mass? What piece of information would allow me to do that? Think back to the very beginning of the semester. Very, very first experiment you did, where you measured volume, and you had the theoretical volume, the volume you thought you were dispensing, and the actual volume. How did you turn those volumes into masses? What did you use? It starts with a D and ends with density. How do I turn a volume into a mass? If density is equal to mass over volume, and I know the density, and I know the volume, how would I get mass? Mass would just be volume times density, okay? So to get kilograms of that solvent, if it's given to you in milliliters or liters or whatever, right, you have to use the density to turn a volume into a mass. You have to use the density to do that. So just get prepared to think about it a little bit differently. Now the numerator is still the same, all right? Moles is still the same. That part hasn't changed. You're going to have to think a little bit more for the molality calculation, though, because of the fact that you're probably going to need to use density. So let's do this one together. You dissolve 2.4 grams of potassium nitrite in 950, with a decimal place, milliliters of water. Density of water is 1 gram per milliliter. What is the molality of the solution? So you're going to have to do a little bit of side calculations before you can even calculate this molarity. Right? What are you going to have to do? Do you just plug in 2.4 as the numerator, number on top? No. What do I have to do to it? Convert it to moles, right? And then what do I have to do with that volume? Now here, if you forget to multiply the density, it won't matter, right? Because the density is 1. So if you forget to multiply by 1, it's not going to mess things up. But you would have to convert that milliliters to kilograms, right? So here's the solution. No pun intended. Right, we're converting grams to moles. We're carrying out extra decimal places because we're going to round at the end. Now the mass of the water is just its volume times the density, right? Because when you multiply volume times density, what? Milliliters cancel, so that gives me units of grams. But the problem doesn't want grams. I need kilograms for a molality calculation. And now I'm able to do my calculation, my final step. Do we understand how to do this? Now again, on this problem, because the density is 1, if you forgot to turn the volume into a mass, it wouldn't mess things up because the volume, the density is 1. But if you're doing anything where the density is not 1, that's an important factor to remember. Do we understand how to do molality? Are you ready to try one for yourself? Of course I am. I can't wait. Bring it on. What is the molal? Notice the difference in terminology there. It's not molar, it's molal. What is the molal concentration of a solution formed when 2.5 grams of glucose, and there's its formula, dissolves in 200 milliliters of ethanol, there's its formula, and its density? I'll pause the recording while you think about this one. Let's look at the solution to this one. So I asked for the molal concentration, so that means it's molality, not molarity, right? Density of the solvent plays a role here, yes? Because how do I convert 200 milliliters to kilograms? I can't do that unless I know the density. So we have to still convert grams to moles of glucose, right? That's not anything new. So we convert grams to moles. We're going to carry out extra digits because we're going to round at the end. Right, molar mass of glucose is about 180. Now to get the mass of the ethanol, that's its volume times its density, right? Because that's 200 milliliters, and that's 0.789 grams per milliliter. Again, we're carrying out extra decimal places. So I got 0.1578 kilograms. Did you? And now we can divide. Now we can divide. Moles per kilogram. And then rounding our final answer to 2 significant figures, because 25 has 2 sig figs, 200 with a decimal place has 3 sig figs. So my final answer is 0.88. Now, again, in terms of units, write a lowercase m, or you could write out mole/kilogram, because that is technically the units as well. Okay, so if you don't want to deal with, is my m lowercase looking enough, you could just write MOL/kilogram. Okay, I will accept either one because they're both correct. If you made a mistake, do you see where you made it? Is everybody good on this one? Moles per kilogram, or you could write lowercase m, either one. Ready to try another one? You'll need me to stay here a little longer. We good, we good, we good? Okay, do this one. What's the molal concentration formed by dissolving 14.9 grams hexane, which is C6H14, in 20 milliliters of benzene, which is C6H6. Has a density of 0.8786 grams per milliliter. Let me pause the recording. I'll give you a chance to work. Let's see the answer to this one. Hexane and benzene, what kind of intermolecular forces would both of those have? Good review question. What kind? London forces, right. Would these two be soluble in each other? Yes, they would. Okay, so we have to figure out the number of moles of hexane we have using the molar mass, carrying out extra decimal places so that we can round at the end. Now we need to figure out the mass of the benzene using the volume and the density. Right? We're told we have 20 milliliters and its density is 0.8786 grams per milliliters. So milliliters cancels, that gives me grams. But I don't need it in grams for molality, I need it in kilograms. So move the decimal 3 to the left, 1, 2, 3. So that's why it's 0.01757 kilograms. Now I'm ready to divide. I came up with 9.84, 3 sig figs. Do we agree? In terms of units, you could write little m, or you could write out MOL/kg. Either one works. We good on this one? Molality is not as bad as I made it out to be, right? It's not that bad. The only thing you have to worry about is you have to make sure you understand how to turn a volume into a mass. And that's the only thing you have to worry about here. And molality is going to come back into the picture in 2 weeks when we talk about colligative properties. Okay, that's why we're spending time talking about it now. Here are 2 more concentrations that are very easy. They are very, very easy. You're not going to break your brain working out these problems. Percent by volume and percent by mass. Okay, percent by volume is volume of solute over total volume of solution. And percent by mass is mass of solute over total mass of solution. Oh, there it is. There's one that's not. So percent by volume is volume of solute over total volume. Okay, so if I say you're dissolving 100 milliliters in 500 milliliters, right? That would be 100 over 600 here. Or if you dissolve 5 grams in 20 grams, that would be 5 over 25. It's the total. We see this a lot when we're dissolving a liquid in another liquid. For instance, if you're making an acetone solution, right? You're dissolving acetone in water. Or when you buy hydrogen peroxide, right? Brown bottle in the pharmacy section, it's a 3% solution, if you've ever noticed that. What are some other things that are in percent? Rubbing alcohol is in percent when you buy it at the pharmacy, right? That's percent. So if you see it's a 6%, or it's a 12%, or it's a 95%, what does that mean? This is how it was calculated. It's either percent by volume or percent by mass. Okay? Percent by volume or percent by mass. No moles, no grams, nothing to worry about. The only thing you have to watch is units. Okay? The volume here needs to match the volume of here. If this one's in milliliters and this one's in liters, that's not going to work, right? Because these 2 units need to be compatible. If this is in grams and this is in kilograms, that's not compatible, right? Because then your units would be grams per kilogram. So make sure your mass has the same units. Make sure your volume has the same units. We see this a lot when we're making solutions by dissolving a liquid in a liquid. That's the most common place you see it. So you do this one. If 10 milliliters acetone dissolves in 190 milliliters of water, what's the percent by volume? I'm not even going to pause the camera because I think it'll take you virtually no time to work this problem. Take about 10 more seconds. We do need to still follow sig fig rules. Okay? Just because it's easy doesn't mean we neglect sig figs. So is this 10 over 190 or 10 over 200? 10 over 200, right? Because it's total volume. Total volume. So 10 is, that's the solute. Total volume is 10 plus 90, which is the 200. And then I round to 2 significant figures, right? Because 10 with a decimal has 2 sig figs, 190 with a decimal has 3. So my final answer is 2 significant figures. Units are percent. And then you just write that V next to it just to show that it's percent by volume. But if you just wrote 5% and omitted that, I probably wouldn't mark you wrong. So long as the percent is there, okay? Gotta have the percent. Do we see how to do this? Easy peasy, right? This one's cakewalk compared to the others. Another easy one coming down the pike, parts per million. Parts per million is mass of the solute over mass of the solution times 10 to the 6th. 10 to the 6th would be a million, right? Again, make sure that your mass matches. If this is in grams and this is in kilograms, you're going to have a problem, okay? Mass of solute over mass of solution times a million. So obviously, you'd be using parts per million when the concentration is very low, right? You're not going to use this for a high concentration. You're going to use this for a very low concentration. True story, last week I'm standing at the gas tank pumping gas. You know, you don't really have a whole lot to do, so you're reading all the labels on the gas pump, because that's what I do. And I looked at the diesel label, and it said ultra low sulfur. And then in parentheses underneath it, it said 15 parts per million max, right? 15 ppm. So that's a low concentration. Right? That's a low concentration, 15 parts per million. In the town that I live in, when every year the city water sends out an inspection report on all the concentrations of all the contaminants that they tested for and what they were. So like, here's what the EPA says it should be, here's what it was when we tested, and it's always in ppm, right? So, you know, the ones like lead and stuff are always 0, which is good. But again, you would use parts per million or parts per billion if you are dealing with a very low concentration. So this is way, 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 way lower than molarity. Right? You would not express something like a molarity in parts per million or parts per billion. It'd be 5 times 10 to the 8th parts per million. That doesn't make sense. You would use small concentrations. The only difference between parts per million and parts per billion is what you multiply by. Right? 10 to the 6th is a million, 10 to the 9th is a billion. So you're measuring contaminant in soil or in water or in air. You're measuring small concentrations, not large concentrations. So you do this one. You're testing soil and a 10 kilogram sample contains 0.0995 grams of lead. I want you to express this concentration both in parts per million and parts per billion. Take a second and do this one. So the calculation is going to be the same. The only thing different between when you get it in parts per million and parts per billion is what you multiply by, right? For parts per million, you multiply by 10 to the 6th. For parts per billion, you multiply by 10 to the 9th. Now, the one thing that you might have had problem with is units, right? It's not 0.0995 divided by 10 because the 10 is in kilograms and the 0.0995 is in grams. And so if these are in different units, your units would not be parts per million, your units would be grams per kilogram, which doesn't make sense. These units need to be the same so that they cancel out. And 3 significant figures, right? So in parts per million, it'd be 9.95. In parts per billion, it'd be 9,950. Same division, the only difference is you're multiplying by a different number. The one thing that could have got you, if something got you, was the units. You forgot to convert kilograms to grams. You could have also converted grams to kilograms. You'll get the same answer. So if you wanted to convert 0.0995 grams to kilograms, you could have done that too. Just move the decimal 3 to the left. You'll get the same answer either way. We good on this one? If you made a mistake, do you see where you made it? Okay, thinking a little bit more this time. When 0.018 grams cyanide dissolves in 8.4 liters of water, the density of water is 1 gram per milliliter, what is the concentration in parts per million? Pause the video while you ponder this one. So this problem isn't really all that difficult. You just have to think, right? Because your units must match. Right now you've got grams and liters. So if you do grams per liter, that's not parts per million, right? So you have to have a way to turn that 8.4 liters into grams, or turn that 0.018 grams into liters, right? Well, I didn't give you any information about cyanide. You could look at its molar mass and all that, but that's not going to help you convert grams into liters. However, you can turn liters into grams, right? You can do that. That's why we look at the density. So 8.4 liters is the same thing as 8,400 milliliters. And if the density is 1, then that means that that 8,400 milliliters has a mass of 8,400 grams. And now we have 2 units of mass. So now we can do it, right? 0.018 divided by 8,400 times 10 to the 6th would be 2.1 parts per million. Even at 2.1 parts per million, I wouldn't want to drink that water. No thanks. Thanks. Do we understand how to do this one? If you made a mistake, do you see where you made it? Units have got to match. That's the big part of parts per million, parts per billion, and percent by mass and percent by volume, right? They all have to be in the same units, because otherwise your answer doesn't make sense. You end up with some units that are just weird. All right, the last thing we're going to talk about today is dilution. This is something I do every semester, right? All the solutions that you have were prepared by yours truly. And so what I do is I make concentrated solutions at the beginning of the semester, and then when it comes time for us to do a lab, then I just dilute them. So that way I'm not making the same lab, I'm making the same reagents over and over and over and over and over. Right, so this is the concentrated solution. We call it the stock solution. So if you see the word stock solution, it just means concentrated. And then if I need a particular molarity for an experiment for you guys to do, I figure out how much of the stock solution I need, and then I just dilute it. Okay? So diluting just puts space in between the molecules. So right now we're all concentrated at these tables. If I said dilute yourselves, right, everybody would just spread out. So you're just increasing this space between the molecules. Adding more solvent, not more solute. So this is the formula for dilution. We're using molarity here. M1V1 equals M2V2. Where molarity and volume number 1 are dealing with the concentrated solution, and molarity and volume number 2 are dealing with the diluted solution. Now really I don't care which one you call concentrated and which one you call dilute, so long as you pair them appropriately. Right? You're going to have before and after. M1V1 equals M2V2. So when you're doing molarity calculations, again, these need to be the same unit, right? These need to both be molarity. And in terms of volume, these need to be the same unit. Now I'll let you use milliliters here if you want, so long as they're both milliliters. Okay, if one's liters and one's milliliters, your answer is going to be garbage. Okay, volume needs to be the same, molarity needs to be the same. This is the one time I'll let you get away with not converting milliliters to liters. On Wednesday, when we start doing solution chemistry, if you don't convert milliliters to liters, you're up the creek. Bad. So if you want to just reinforce the habit of always converting milliliters to liters, that's a good habit to be in. Okay? But in a molarity dilution kind of calculation, if you forgot to do that, it would not sink the ship so long as they're both the same. But as I mentioned, starting on Wednesday, when we do solution chemistry, solution stoichiometry, if you don't convert milliliters to liters, it's game over for your calculations. Okay? So out of good prudential practice, if you want to go ahead and get in the habit of converting all volumes to liters, I really encourage you to do that just so that your mind automatically thinks, keep everything in liters. Okay? But ultimately, if you didn't on these molarity ones, as long as they're the same, it won't hurt you. So let's do this one together. How many milliliters of 5 molar potassium dichromate solution must be diluted to prepare 250 milliliters of a 0.1 molar solution? So part 1 is just a calculation. And then part 2 is where the rubber meets the road. What would you actually do to prepare this solution? Because if I'm prepping a lab for you and I can calculate how much I need, well, that's great. But if I don't actually do it, you guys can't do your experiment, right? So first we're going to calculate what we need to measure out, and then we're going to talk about what we actually do. Because what you calculate and what you do are going to be two different things. So how many milliliters of 5 molar potassium dichromate? The identity here doesn't matter, right? Because we're not going to be converting it to grams or anything. Must be diluted to prepare 250 milliliters of a 0.1 molar solution. So what I recommend that you do is list your variables, just like you were back in high school. List out all your variables. Okay, the reason why I encourage you to do this is so that you don't plug in the wrong number in the wrong place. The M1 and V1 deal with the more concentrated solution, right? 5 is greater than 0.1. Do we agree? Yes. So it's the M1. This is the final. I want the diluted solution to have a volume of 250 mils and a molarity of 0.1. So listing out my variables really helps keep you from plugging into the wrong place. Right? V1's what I'm looking for. Do we all agree? Now we're just plugging into M1 V1 equals M2 V2. I didn't show the calculation because I think everybody in this room can do that successfully. Right? You'd say 5x equals 0.1 times 250. So 5x equals 25. I think everybody's good on that part. I hope. Two significant figures, right? 2 sig figs, 2 sig figs, 2 sig figs, therefore 2 sig figs. So that's part 1. That's answering the question, okay, I go back to my big bottle and I take out a 5 milliliter sample. Right? That's part 1. That's how much I need to take out. But what do I actually do if I want to make this solution? Do I just sit there and hand you 5 mils and be like, here you go, guys? Right? No, I actually have to dilute it. So now part 2 asks, how much water am I going to add to this 5 mils? How would you figure that out? You look at the what? I want my final solution to have a volume of 250 mils, right? If I take out a 5 milliliter sample of the concentrated solution, how much water do I need to add to it to get the total volume up to 250? 245, right? So that's part 2. Part 2 is the practical part, right? So you take 5 mils of the concentrated solution, and then you'd add water to get that total volume up to 250. Okay, calculating this volume is only half the battle. You do need to actually do it. How do I know how much water to add? I just look at the final volume. What do I want my final volume to be? Okay, well, I want it to be 250, so I just say, well, add enough water till it's 250. All right, so in this case, it would be 245. We good? Does this make sense? Got one for you to do, and then that'll be where we stop. So, last problem. Plug through, you can do it. If 10 milliliters of a 10 molar sodium hydroxide stock solution is diluted to 250 mils, what is the concentration of the new solution? SOLN is just shorthand for solution. I'll let you work that one. Now here again, just want to point out, these 2 units of volume are the same. So if you didn't convert milliliters to liters, there's no consequence. But if you want to be in a good habit, the good habit is to always convert milliliters to liters as your default setting. Because like I said, once we start talking about solution stoichiometry on Wednesday, yes, stoichiometry comes back, and better than ever. If your milliliters are not in liters, it's going to be a problem. Okay? But here, if you didn't do that, it's no big deal. So we're listing our variables. Our final answer is going to have how many sig figs? 2 or 3? 2. Right, 2 sig figs. Now always ask yourself if your answer is reasonable. The original concentration was 10, and we diluted it to 250. Does a molarity of 0.4 seem reasonable? If the molarity somehow goes up, then you know you did something really wrong. Okay? So that's where we're going to stop for today. Have a good rest of your afternoon, and I will see you on Wednesday.